Uh, Welcome everybody. We have two theory talks today. Before I get on to start the seminar with Daniel's seminar, let me just announce that next week at the same time we will have Luca De Medici and Brian Anderson giving the talks. So with that, Daniel, welcome, and the floor is yours.
Okay, well, thank you for inviting me and giving me the chance to present this work. And also thank you to all the organizers for arranging this whole seminar series. It's been very interesting and I'm learning a lot from it. So what I'm going to talk about is a proposal for the superconducting state in monolayer iron selenide. And this proposal is actually from a couple years ago, but I'll tell you some updates to this, in particular with respect to some realizations we've made for the effective theory of the fermions that participate in pairing in this monolayer. And so there's been some updates in that context, also related to work actually done in rice. So what I'll start with is just a quick introduction to the monolayer iron selenide, which I think is not that necessary. Then I'll spend a reasonable amount of time talking about the normal state and a realistic symmetry-based theory for the fermions participating in pairing. And the reason for this, and the reason that we need to make a symmetry-based theory, is that we've seen in the seminar series that a lot of so the density functional theory does an okay job in understanding these materials, but not a great job. And so we get some insight, but some band orderings are changed, etc. And that actually means that we should rely on theories that are based purely on symmetry with as much experimental input as possible. And I'll talk about how we construct such a theory in this case here. And then I'll couple these fermions in a very standard way to magnetic fluctuations. And this will give rise to a D-wave superconducting state. And I won't spend much time discussing this because it's actually very standard. But the interesting thing about this D-wave state is that it's a nodeless D-wave state. And typically we would have expected this D-wave state to have nodes, much like as we see in the cuprates. And so then I'll turn to briefly an explanation for why that is the case. In particular, when we have nodes, we can assign topological charges to these nodes. And the reason these nodes disappear is because nodes that are close to each other in momentum space have opposite charge, and so they can annihilate. And then finally, I'll talk about some STM evidence for this proposed nodeless D-wave state. Okay, so let's begin with just an overview of superconductivity in the monolayer. It's an interesting material because it is the highest TC in the iron-based superconducting family, and it also shows some fascinating differences with respect to other iron-based superconductors. And so in particular, we have this idea of the standard theory for an iron-based superconductor. That is that we have these hole pockets at the gamma point and these electron pockets at the M point, and we have some repulsive interpocket scattering mechanism. And this repulsive interpocket scattering mechanism gives rise to a plus-minus state in the superconducting state. What's interesting in the context of the monolayer is that we don't have these hole pockets, we only have these endpoint pockets. And even more interestingly, if we look at these endpoint pockets, and I'll talk about this in a little bit more detail, these electron pockets, these look a little bit like, well, these look like two overlapping ellipses. And if we focus on one of these ellipses, then there's some nice ARPES data that measures the gap as we move around this ellipse. And we see that it's fully gapped. And so at first glance, this looks like a usual S-wave superconductor, and there have been suggestions that electron-phonon pairing is important in generating this superconducting state. But here I want to focus on the possibility that electron-electron pairing is most important, and how can we understand what is seemingly an S-wave superconductor in the context of some repulsive electron-electron pairing mechanism amongst these endpoint bands. Okay, and as a bonus, when we look at this, we'll see that we can come up with a very natural explanation for this gap anisotropy that is seen, where the gap is large here and smallest here. Okay, so let me turn then to this effective theory for the quasi-particles near the endpoint. First, look at some experimental results, so some ARPES data. So what does ARPES see? Well, it sees near the endpoint, it sees what looks like two parabolic bands. And these parabolic bands gives rise to these approximate ellipses that are orthogonal to each other that overlap. And in practice, where these ellipses overlap, we would actually expect to see some sort of band avoided crossing. And so we wouldn't expect a true overlap, but some avoided crossing here. And what these ARPES experiments tell us is that this avoided crossing must have an energy scale that is less than 5 millielectron volts. And that's in fact why we see something that looks like these two ellipses. Okay, so I want to talk about the theory near the endpoint, and a very important aspect of the monolayer iron selenide is that it's a non-symmorphic space group, and this strongly affects the states near the endpoint. And so here I've taken, this is well discussed in this PRB paper from 2013 in the context of iron arsenic-based materials, and I've actually taken this figure from their paper. And the key point is, so here is the structure of iron selenium. So A and B are the iron sites, and these crosses and dots are the selenium. So we have seleniums that sit above and below this iron square lattice plane, and all the iron are on the same plane. And because of the selenium, these two iron are inequivalent. But you can also then look at the symmetries of this. In particular, let's focus on a mirror symmetry here, this sigma X symmetry. You can see that this mirror symmetry takes the seleniums to the seleniums and the irons to the irons. And so it is a symmetry. In particular, we don't need to follow this mirror reflection with any translation. However, if I look at another mirror symmetry through the C-axis, then through the C-axis, the selenium that sit on top of the iron layer go to below the iron layer and vice versa. And so these seleniums change position. And so for this to be a symmetry, I need to follow it by a translation from here to here. And so this mirror reflection must be followed by a translation to correspond to a symmetry. The fact that we have some mirror symmetries that are not followed by a translation and some mirror symmetries that are followed by a translation tell us that this space group is non-symmorphic. And that has important consequences for the structure of the theory, especially near the endpoint, as I'll talk about in the next slide. One other thing that's going to play a role in this K.P theory is inversion symmetry. And here the inversion symmetry sits between these two iron sites, which these two iron sites are inequivalent. I should mention, I'm always going to be talking about a 2 iron unit cell in this talk, occasionally referring to the 1 iron unit cell language. All right, so this inversion relates the 2 iron sites and also relates these 2 selenium sites. Okay, so let us now look at what DFT theory tells us about the states near the endpoint in this material. And there's a few important features I want to highlight. This is DFT results produced by my colleagues here at UW Milwaukee, though many people have actually come up with these results. But one thing you can see right away is as we look at these bands where they meet the endpoint, you can see that bands merge together. And quite generically, because of the non-symmorphic symmetry, all these endpoint electronic states are 4-fold degenerate. They have 2 orbital and 2 spin degrees of freedom. And so that's going to play an important role in describing the low energy electronic structure here. Secondly, if we take this band structure seriously, you see that if I'm looking at states that cross the chemical potential, then I have states that come from this endpoint, which I call M1. So these 2 states. Then I also have a state that comes from this endpoint called M3. And for those of you familiar with the band structure calculations, you're well aware that M1 is formed from XZ, YZ orbitals, and M3 from X squared minus Y squared orbitals in the 2 unit cell, which is XY in the 1 unit cell. And I'm going to talk about this ordering of M1 and M3 in a minute. But first, let me point out one other feature that shows up in this in these band structures. or in this theory, and that is that if we look at the electronic orbital representations right at the endpoint, there is an important feature that also shows up related to the parity center I mentioned in the last slide, and is that the two partners, the two orbital partners, have opposite parity generically. All right, and so I've illustrated that by showing the x squared minus y squared electronic states in the orbital channel at the M3 point, and here's the two degenerate partners. And so I put the inversion symmetry I mentioned before between the two sites, and you can see here that under this inversion, we get a phase change from the x squared minus y squared orbital here to that here. Conversely, in the other partner, the phase stays the same. So this is odd parity, and this is even parity under that inversion symmetry. Okay, so now let me turn to this notion that we need to include these two endpoint representations to describe the states at the chemical potential. A consequence of that is that you generically have this crossing of this bands from M1 and M3, and you should be able to see this crossing in ARPES measurements. And this crossing is allowed by symmetry when there's no spin-orbit coupling, because these bands belong to different representations, and so they're allowed to cross. But in practice, as pointed out nicely by the Rice group and collaborators, this band crossing is not seen in iron selenite. And so if we want to come up with an effective K.P theory, we need to explain why that is the case. And so, as I mentioned, the explanation for this is already understood. The band crossing becomes avoided when the order of these two switches. So in the DFT language, and this is, by the way, nicely explained in these references here. And there's a presentation at the last March meeting from Ming Yi, which goes into this in some detail. And so you can really see this in some detail there. But the key point is that if we switch this order M1 and M3, then the band crossing that happened is, well, no longer there, but there's another analogous band crossing. But in this case, the bands that cross in the analogous case belong to the same symmetry channel. And because they belong to the same symmetry channel, they become avoided, and they result in a band structure that looks like this. And so now you see that this band crossing no longer exists and won't be seen. And this is very consistent with the ARPES data in many of these iron selenium based materials, not in the iron arsenic based materials. And this has an important consequence for the structure of the effective symmetry based model. If we're looking at such a band structure, it's clear that only a single endpoint representation is needed to describe the states. All right, and so that's what I will be using here. And I'll talk about results in the context of that single endpoint representation. Okay, so without going into the details, let me now turn to the resultant effective symmetry-based theory. And let me explain the different terms that show up and how we can understand that in the context of the results we've seen so far. All right, so here is the general symmetry-based Hamiltonian. And I've done small momentum-based expansions for these coefficients for this theory. And we get generically three terms. One is just a usual parabolic dispersion, which is the same for both orbital channels and spin channels. And then we get this kx, ky dependence. And that shows up with this orbital tau z channel. So it's opposite for one orbital and between the two orbitals. And this generically leads to our two ellipses. We get one ellipse from the positive side, kz, kx, ky, and then another orthogonal ellipse from the minus kx, ky. And so without this term here, we would get two overlapping ellipses, much like what is seen in the ARPES data. But then, of course, symmetry allows this other term, and that's a spin-orbit coupling term. And it is, for people familiar with spin-orbit coupling, this should come as a bit of a surprise because it's linear in momentum. And the reason this is allowed to show up in this theory is because of this point I made on the last slide, that the orbital representations at the endpoint are made up from orbitals of different parity symmetry. So even though this term breaks parity symmetry, there's an orbital operator that corresponds to that, and that allows this term to exist in the theory. And this term is the term that leads to the avoided crossing between the two ellipses. And I tried to show that here. I put in a small spin-orbit coupling. And so you get this avoided crossing here coming from this spin-orbit coupling term. And this looks almost like two ellipses overlapping, but this is something that would be consistent with the ARPES data. Okay, so that's the effective K dot P theory. The one other thing I want to point out is that this is complete in the sense that we need to add no other orbitals, no other polymatrices tau or sigma. No other polymatrices tau or sigma are allowed by symmetry. And so this has all the terms that are allowed by symmetry. And so we can be confident that we're doing a good job in explaining the normal state properties here. Okay, and then here in MEV are some parameters that correspond nicely to what the ARPES data gives. Okay, so with that normal state property, normal state theory in hand, let's turn to the superconducting state. And here I don't want to spend too much time because a lot of this is a relatively old story. But in the two-dimensional monolayer, we can't actually easily figure out what kind of magnetic fluctuations or what kind of fluctuations there are. And so the only way to get some insight is to look at three-dimensional analogs of this. And so we can look in particular at the three-dimensional iron selenium. And then here, it's been shown that if we are sitting up at temperatures above the pneumatic transition, then we have both nail pi fluctuations and also stripe pi0 fluctuations. And here the notation is that of the 1 iron unit cell. Also, if we look at this material, which has iron selenium layers that are separated, relatively well separated apart, this also shows pi and pi0 fluctuations. So experimentally, we have evidence for both these types of magnetic fluctuations. And finally, my colleagues here in Milwaukee have also done DFT studies which find that generically we do have both these types of magnetic fluctuations present in DFT as well. Now, one issue with the theory I just wrote down is that the Fermi surfaces are small. And so we expect that the magnetic fluctuations that are relevant should be small q fluctuations. And naively, pi and pi0 are large q fluctuations. But the key point is that this notation, pi and pi0, comes from the 1 iron unit cell. And if we express it in the 2 iron unit cell, the pi nail fluctuations become small q equals 0 fluctuations in the 2 iron unit cell and can serve as a pairing mechanism for the fermions there. And so here's a picture of that sort of standard nail antiferromagnet. So let's use this as the pairing mechanism and see what happens. And so that's what I'm presenting here. So here's our normal state Hamiltonian. And the first thing we do is just ignore the spin orbit coupling because that's the most natural thing to do. And then when we solve the theory without spin orbit coupling and add these nail fluctuations, we find a spin singlet D wave state. And this spin singlet D wave state has a very interesting orbital structure. In particular, it's plus on one of these two orbitals and then minus on the other of these orbitals. And so it has this sign change between the orbitals. And so we call it orbitally non-trivial. And I think you'll hear more about these orbitally non-trivial states in the next talk, actually. And so, and also what's interesting about this state is, as you can see, if I do a rotation about here of 90 degrees, then I switch the plus and minus. And so this is a D wave gap. And usual symmetry arguments would say we must have nodes in this D wave gap, but we see no nodes here. This is fully gapped everywhere. And just for contrast later, I'm going to consider an orbitally trivial usual D wave so that we can see how this differs from this usual D wave in certain aspects. All right, but let's now talk about these nodes. Well, one thing I did is I turned off this spin orbit coupling. So let's turn it back on and make it large and see what happens to the superconducting spectrum. So that's what's being done here. I've made this spin orbit energy scale very large. I made it 16 MeV, and I told you from experiment it should be less than about 2 MeV. But when we do that, indeed, nodes reemerge. And so we have this situation now that we have nodes with large spin orbit coupling and no nodes with no spin orbit coupling. And so we want to understand how we get a transition between the two of these. And so here, I'll quickly go over an argument for that. In particular, we can use a nodal classification, a topological classification of these nodes. And the key point is that these nodes are protected by a time reversal times inversion symmetry. And in this particular problem, it gives the nodes charges of plus and minus 2. And what matters is the distribution of these plus and minus 2 charges throughout the Brouwen zone. And let me show you how that matters. So here's the usual D-wave superconductor. And so here, these are the nodes that are relevant to us. So red is plus, blue is minus. And here you can see 2 plus 2 nodes sit close to each other in momentum space. And as we decrease the spin-orbit coupling, these 2 nodes will approach each other. But you can see that there's in no sense will these nodes annihilate in this orbitally trivial superconductor. But in the orbitally non-trivial case, we find that the nodes that sit close to each other have opposite charge. And so what happens as we reduce the spin-orbit coupling is that these opposite charge nodes approach each other and can eventually annihilate. And it's the annihilation that gives rise to a fully gapped superconductor. And so I should mention there's a whole series of ideas related to this presented with similar states in these papers here. Okay, but that's the essential explanation. Because of the orbitally non-trivial structure, we get these nodes that can easily annihilate. So now let us bring down the size of the spin-orbit coupling and see choose something more consistent with experiment to see what we get. And that's what I'm doing here. And so here I chose a spin-orbit coupling that's 2.4 MeV. And this is consistent with experiment. And what we see now is we have gap minima where the node should appear. So that's very natural. And if we compare that with the ARPES data, we see that we get some very nice agreement. The gap maxima sit in this direction at 45 degrees where the nodes would have appeared, we have gap minima. And we can ask the question, when do the nodes disappear? And it turns out they appear when the spin orbit energy scale is the same size of the gap. So when the spin orbit energy is less than the gap, we have a generically nodeless D-wave state. It looks like I'm coming close to the end of my talk, but I have just this one last slide to present, which comes from my colleagues at West Virginia University, where they looked for experimental evidence for this nodeless D-wave state. And the key way to do that is to try to look for this phase difference between these electron pockets. And this is expressed now in the 1 iron unit cell. And the key point is that they were able to find different superconductor vacuum interfaces with orientations that are 45 degrees with respect to one another. And so here, if they look at a 0, 1, 0 edge and they measure the gap as they approach that edge, they found that the gap doesn't change at all. However, at a 1, 1, 0 edge, they found that initially the gap doesn't change, but as they get within a coherence length of the vacuum superconductor interface, the gap starts to suppress. And the way we understand that is for the 0, 1, 0 edge, a quasi-particle scattering off the boundary scatters from a gap of 1 sign to a gap of the same sign, so there's no destructive interference. However, for this 1, 1, 0 edge, we have a quasi-particle scatter from a gap of 1 sign to a gap of the opposite sign, which tends to suppress the Fermi surface. And so this observation of suppression for one edge, but not for the other, is consistent with the nodeless D-wave state. All right, so that brings me to my conclusions. And I do think I went a couple minutes over time. And so what I'll do is I will just leave these up here and then open the talk to questions.
Thank you, Daniel. We have plenty of time for questions, comments. I see Ilya.
Yes, thank you, Daniel. A very nice talk. I have a question regarding, a similar system, because you mentioned that that you can have this electron intercalated, and this is about materials. So for them, at least from what experiment I've seen, the conclusion was that you have most likely this sign changing S plus minus state. I guess this is, in your theory, would depend simply on the strength of the spin orbit coupling. So if you increase the spin orbit couplings, then probably you will have a transition to the sign changing S plus minus gap between outer and inner pocket, right?
In principle, this is possible. So the suggestion is that you have an outer and an inner pocket, and you have a plus gap here and a minus gap here.
Yes.
Yeah. So in principle, yes. I mean, we studied the theory with small spin orbit coupling, and indeed, when you increase the spin orbit coupling, you will get different states. And amongst those is indeed a sign changing plus minus state. Yeah, so this might be interesting, for example, when you put tellurium in the system, spin orbit coupling will naturally increase. And so FeTe-Se systems might actually switch to such a state.
Right. So the reason I'm asking is that in this lithium OH intercalated with iron and this electron intercalated with the Fermi surface topology looks very similar. As this claim was that the gap is actually sign changing as plus minus. And we studied that, and it turns out that if you increase the spin orbit coupling, so the model is very similar to yours, that you will get it. I have another question sorry, may I?
Yeah, go ahead.
Another question is, in principle, you don't have also an inversion. So the spin orbit that you included is, of course, the one because of this properties from the M1 to M2 point, from these different endpoints. But in principle, you can also assume that there is also a true rush pattern. The question is it included somehow in this description, or it should come on top?
Yeah, so originally when we studied the problem, this was the actual issue we were most interested in. But when I talked to my DFT colleagues, they told me that the effect of the interface was not substantial on the electronic structure. And so we really couldn't see big results coming from this additional Rashba term. And so in the end, it didn't seem reasonable to choose it to be necessarily big. Now, in principle, it could be tuned, for example, by applying electric field across the system or something like this. But the theory we've presented is without this coupling. It's possible to ask what changes when you add this Rashba spin orbit coupling, and we've done that. Qualitatively, many things stay the same, but of course, you'll get some small differences as long as that term is sufficiently small.
Okay, thank you very much.
Thank you. I think Igor Saliziaka has a question.
Thank you, Jamal, and thank you, Daniel, for an excellent talk. Just a simple question to sort of precise the exact origin of spin orbit, because you were referring at the beginning of the talk to iron orbitals, but then obviously spin orbit, as you've mentioned, comes from ligands. So can you just explain that aspect?
Yeah, I meant to clarify this in the talk and I forgot. When I say spin orbit, I mean this term because it's the only term that looks like spin orbit in the symmetry-based theory. But you're right, the spin orbit we're all familiar with is an L.S that is local on the iron sites, right? And then it depends on the orbital nature of these orbitals that make up the electronic states. And actually, this is a highly non-trivial issue in this. Let me come back to this picture here. So here we have some idea. This is without spin orbit coupling. This is the DFT structure. And we see that we have these XZ, YZ orbitals and these XY orbitals. But then we make this claim that we switch the order of these orbitals. And so a consequence of that is that these bands are now actually fairly strongly mixed between XY and XZ, YZ. And the intrinsic spin orbit coupling that comes from the iron sites plays a role in mixing these up. And so strictly speaking, and I didn't really speak about this, these orbital states that make up this theory are actually some sort of two pairs of Kramer's degenerate states, which are any admixture of the orbitals that we see. And the spin that we talk about is strictly speaking pseudospin, not true spin. And so here, this is a pseudospin spin orbit coupling in this language. I mean, the one thing I do want to point out is that this K.P theory is insensitive to the inclusion of this atomic spin orbit coupling. It has the same structure no matter what the spin orbit coupling is, and no matter what the makeup of the states that give rise to this. But the interpretation then of what this operator is very different than what you're talking about. And in fact, even what these orbital operators is very different than what we're used to. But again, I'll point out that this is all captured within this symmetry-based theory.
So Daniel, I guess you're saying that this spin orbit coupling in principle is different from what one would extract from the splitting of the XZ and YZ states near gamma.
Yes, it is. Mm-hmm. So that splitting plays a role in defining the pseudospin and the orbital states. Yeah, okay. And this spin orbit coupling is related to that, but it's, of course, if you turn that off entirely and have no spin orbit coupling in your theory, this term also disappears.
Right. Mm-hmm.
So it comes in.
So basically, am I right saying that these effective bands that you're considering, they actually do include some admixture from p orbitals, such that a transferred spin orbit from the ligand is also to an extent included in this effective spin orbit coupling?
Yeah, so strictly speaking, and that's also a good point. Yeah, so indeed, these x squared minus y squared orbitals do admix with the pz from the selenium, and giving rise to the ligand states you're talking about. And so they, in principle, also include these pz orbitals. And I took that out just in this picture to make this a little bit easier to look at, but you're right, yes.
Yeah, thanks, because that just connects to change of spin orbit with going from selenium to tellurium.
Yes, exactly, exactly. That's a good point.
All right, any other questions, comments? Okay, we have a question by Dipmaria Chakraborty, please.
Hi, Daniel. I had two questions basically. Do we expect a transition from node to nodeless or vice versa just by adding disorder?
Yeah, so I didn't, so we do expect some transitions from node to nodeless. Let me go back to the slide that showed this critical condition here. So when the spin orbit energy scale becomes equal to the gap, then indeed we will get a transition. And of course, the gap is generally temperature dependent. So already with temperature, as temperature increases, once the gap magnitude becomes around 2.4 MeV, we should see a nodal superconductor. I mean, how such a thing can be observed experimentally would be is difficult, because we're already a substantial, we're very close to TC. So there are many other effects to worry about. But in principle, also adding disorder to the system can reduce gap magnitudes and bring us closer to this critical value. So yes, there can be such a transition.
And a second related question is, then can we distinguish between node and nodeless D wave by seeing its evolution as a function of disorder?
Yeah, in principle, yes. If you do manage to reduce the gap magnitude, I mean, it is a substantial reduction, right? You need to reduce it from 11 MeV to whatever, 2.2 MeV or so. And then you can look at the thermodynamic properties of such a state, and assuming that that can be properly characterized by some average disorder uniform state, then those thermodynamic properties would indeed look like a D-wave superconductor with nodes, right? So you would see line nodal behavior, but there's a few ifs along the way, I think, in doing that. But in principle, the answer is yes.
Okay, yeah, thanks.
Okay, we have another short question. We can go with that. If not, let's thank Daniel one more time. Thank you for a nice talk.
Thank you.
So we move on to